All right, so the kinetic molecular theory is just the theory that governs how gas particles should be thought of as moving and interacting with each other. So there's a couple main points to this thing. There are five actually. So number one, gas molecules are in continuous random straight line motion. Number two, the volume of gas molecules is negligible, so we don't really have to worry about how big the particles are themselves. Number three, intermolecular forces are negligible as well for gases. And number four, gas collisions are perfectly elastic, meaning kinetic energy is conserved with each collision. And so what we're going to talk about is the fact that it's not necessarily the case all the time. And you've seen this equation before, van der Waals equation. We're not going to be using this because we don't calculate this on the AP exam. But you should know why it leads us to having pressures below what the ideal gas law says that we should have. And so it's just basically a little twist on PV equals nRT. And you can see here we've got number of moles squared times this value A over volume squared added to pressure. So where pressure would normally be, we have all this extra stuff. And then we have this number of moles times another constant B subtracted from volume instead of just having volume. So what are those things? Well, if we look at a table of gas constants, van der Waals constants are called, you can see some of your more polar molecules have larger values for A. And that's going to cause them to deviate more from what we would expect if we just solved for pressure using the ideal gas law. So the larger the A value, the bigger the deviation. So like, for example, ethanol, a lot of intermolecular force there because of hydrogen bonding and also because of the size of the molecule. It's going to lead to it having a large attraction. I don't think that A actually stands for attraction, but that's kind of how I think of it. And then we also have to think about the volume of the particles themselves. In other words, if we compare a real gas to an ideal gas in a container that has a real gas in it, we say the volume of the container is the volume of the gas, but in reality, the volume of the container, we would have to like subtract all the tiny little volumes of the gas particles to be completely accurate. So that's what that's taking into account there. And you don't really have to use van der Waals equation, but you should know how to anticipate when it would result in giving us a big deviation from the ideal gas law. So for example, you might be asked a question like this, and this actually was on the little packet I gave you. It was one of the questions. Which would deviate most from the ideal gas law and why? Or most from an ideal gas, or which is the least ideal gas, I guess you could say, and why? And so you actually only have one of these over here on the table, which is fine, because really all I need you to understand is the concept. The concept is that the more polar the molecule is, the more it's going to deviate from what we expect an ideal gas to do and how it's going to behave. So if I were to ask you what's the most ideal gas we can think of, it's probably going to be helium, maybe hydrogen. They're both really, really ideal. You can see here, hydrogen is a little bit more attractive because it's a molecule rather than a single atom. So helium is going to be our winner in terms of which one is most ideal. Okay, in other words, least attractive forces, also not a very big volume for a helium atom. So among these guys, think about which one you would expect to deviate the most from ideal gas. So I would say SO2, because it actually does, if you draw the Lewis structure, have a bent structure, and therefore it's going to be a polar molecule. And it also has a mass of about 64 AMU. Carbon tetrachloride is nonpolar, but it is very large. So the London dispersion forces might be pretty large for that one. So I would go with SO2, and I would expect that to be the answer. CCl4 is probably a close second just because of the size of the molecule. But and chlorine is a relatively large molecule. Cl2 is relatively large as well, but nitrogen would be the most ideal of all four of these gases. Okay, the next thing we want to look at is the fifth and final tenet of the kinetic molecular theory, which says that average kinetic energy is proportional to Kelvin temperature. So at a given temperature, molecules of all gases have the same kinetic energy. So this is what's called a Boltzmann distribution, or Maxwell-Boltzmann distribution. And so we have two different graphs. They're both kind of the same thing, kind of different. Along the y-axis, we're just talking about the number of molecules, or excuse me, or the probability of finding a molecule that is traveling at a given speed. So speed is on the x-axis. So you can see here we've got, for this left-hand graph, four different gases. And the one that is, these are all noble gases, so they're all nonpolar. And so the one that is the least polar, because it has the smallest size, is helium, right? So helium tends to travel faster on average. So technically the peak is not quite the average, but it's pretty close to it. But on average, a helium atom is going to be traveling much faster than a neon or an argon, or certainly a xenon, okay, at a given temperature. Now here on this right-hand graph, we're looking at the same gas at three different temperatures: cold, room temperature, and hot. And so you can see that obviously they're going to speed up quite a bit. The reason that the hot gas has a flatter curve is because there's more interaction or collision between particles, and so therefore more transfer of energy. So therefore you have more of a spread of different speeds that the particles have, because there's more interaction. Cold gases, even if they are gases, aren't going to interact as much, and so you're going to have a narrower range of speeds. The same thing is true for our polar molecule, or I'm sorry, our larger xenon atom. I started to say polar. It's more polar than helium, right? But it's still technically nonpolar, because it does have those big London dispersion forces because it's a large atom. So anyway, its range of speeds is narrower because there's less interaction between the particles, even though they're all at the same temperature. Because it's heavier, they're bouncing into each other less, so you get a narrower distribution. Really, the big thing, though, is that you just understand that the speed is going to be much slower for our larger molecular atom. Okay, and then the final thing that we want to talk about is gas movement, diffusion, and effusion. So we talked about this if you took honors chem. Basically, diffusion is just gas mixing with other gases. Effusion is gas escaping from a container, like a puncture in a tire. They both are going to be determined or governed by what's called Graham's law, which basically is just saying that if you want to compare the relative velocities of two gases, so that we can say that one gas is 1.5 times faster or slower than the other, we say the relative velocity of gas A over B, or over velocity of gas B, is equal to the square root of the molar mass of B divided by the molar mass of A. So because we're flipping and having B on top, that tells us we have an inverse relationship. Okay, so let's take a look at a problem from the packet I gave you. This is I said number 2, but actually I moved it, so don't pay attention to that number 2. So it was one of the later problems in the packet. But anyway, it says the diffusion of carbon dioxide gas was 105 seconds, meaning it took 105 seconds for the CO2 to travel across the room, or whatever the distance was. For gas X, the same amount of gas requires 126 seconds to diffuse. What's the approximate molar mass of the gas? So what we're doing is we're saying we know the molar mass of carbon dioxide. We're looking for the unknown molar mass, and we're going to use their relative velocities to do that. Now, for this problem, it's a little tricky because you're not given the relative speeds or velocities. It's not saying that the carbon dioxide is 1.2 times faster or anything like that. But what they are telling you is the time. So you just have to remember that velocity is proportional to the inverse of time, or inversely proportional to time. So as time gets longer, that must mean that that gas X is moving slower, has a smaller velocity. Okay, so with that in mind, for what we're doing, since we're only concerned with relative velocity, we can get rid of the proportional sign and simply say that the velocity is equal to 1 over time. Because we're not interested in the absolute speed in meters per second or miles per hour. We simply want to know how fast they are relative to one another. So that's why it's okay to just take the inverse of time and call that the velocity of each gas. So, for example, if CO2 took 105 seconds to diffuse, we're going to call the velocity of CO2 1 over 105. And again, we're not worried about units because these are just relative numbers. And then I'm going to do the same thing with the unknown gas, which took longer, and predictably, of course, we get a slower speed, a smaller number for relative velocity, right? So now it just becomes a matter of plugging into the equation. Now notice I put the relative velocity of CO2, 0.00952, on top, so I'm calling CO2 gas A, and it doesn't really matter which one we make gas A. I'm calling the unknown gas, which had this velocity, I'm calling that gas B, putting it on the bottom, but be careful. When you go to the other side with the molar masses, B goes on top. And so that's why I put an X up there, because we don't know the molar mass of gas X. Okay. And then I put the molar mass of CO2 on bottom. And so then it just becomes a matter of solving. So X is inside of the radical. We're going to square both sides. We get, once we do that, we get this. And then we just have to simply multiply both sides by 44.01 AMU, we get an X of 63.3 AMU, which is predictable because the gas was slower, so it makes sense that it would be larger.